Welcome to the second part of the lecture on image segmentation. In part one, we've talked about many different methods for image segmentation. And we're not going to talk about more methods for segmentation, but rather we're going to talk about methods to improve segmentation. Because the results of image segmentation methods are hardly ever perfect, and you need to do something about it. And we're going to look at a particular type of methods to do this, which is called mathematical morphology. What can you do with these methods? For example, clean up background noise. We've talked about this in the previous lecture. There may be lots of false positives in the background, but also lots of false negatives within the object. So how do you reduce object noise in the segmentation? Another thing that happens very often is that segmented objects are touching. And so they are considered as one object by the connected components labeling algorithm. You need to do something about this. You need to separate objects before running the connected components labeling algorithm. And other things like how do you close holes, how do you extract object contours, how do you compute distances in segmented images, for example. This can all be done by clever mathematical morphological operators. There are two branches. The first is binary mathematical operators. That's what we're going to start with. That is for binary images, and that's usually used for post-processing segmentation results. And the other branch is grayscale mathematical morphology, which applies to grayscale images and is usually applied as a pre-processing step to make segmentation easier. Both types of operations, binary and grayscale mathematical morphology operators, are nonlinear image processing techniques based on set theory rather than calculus. So we're going to have to talk a little bit about set theory and representing images as sets. Let's have a look at this binary image, for example, where white is foreground and black is background. So these are the object pixels. We can represent this image like this. We can visualize it with white and black pixels. An alternative would be to look at the images as a matrix of zeros and ones, where the ones are object pixels and the zeros are background pixels. But you could also look at images as sets. I could write the image as a set of all the image coordinates that belong to the objects. That would be these coordinates in this case. Once an image has been represented as a set of coordinates, you can apply set theory and set operators, and that's what we're going to talk about. But of course, for us to interpret the results, this is not very handy. And so in the examples I'm going to show throughout this lecture, we're going to still represent sets as images, just to visualize the results. That makes it much easier for us to see what is going on. The first thing we need to do is define a couple of set operators, and I think many of these things will be familiar to you, so this is just a little refreshment. If we have two sets, A and B, so that is a set of coordinates, and the index is I, you have NA coordinates in this set, so you could say NA pixels, and you have NB pixels in this set, and these coordinates AI and BI are defined on the integer grid in n-dimensional space. It works for any dimension, but the examples I'm going to show you will be mostly two-dimensional images. So what kind of set operators do we have? For example, translation, shifting the set, written like this, A subscript X, where X is the shift. So that's another coordinate, you could say, or a displacement vector in the same space. And A sub X is the set of all coordinates defined as follows. CI is AI, so these are all the coordinates from the original set A, but with a certain offset added to it. So that is the shift or the translation. Reflection, which is written like this, A superscript R, is the set of all pixels, all coordinates, which are the original coordinates, but then negated. So you get the negative coordinates. Essentially what this does is mirroring the set around the origin. Then the complement, A superscript C, that's the set of all points, coordinates, pixels that are not in A within the image domain. Then you've got the union. If you've got two sets, you can take the union of the sets, which are all the pixels that are either in one or in B or in both. Of course, you can also compute then the intersection. That's all the pixels that are in A and in B. And then you can compute difference as well. A minus the set B, which is all the pixels that are in A and that are not in B. You could also do the reverse, of course, B minus A. That will be all the pixels that are in B and not in A. And finally, the term cardinality is often used in set theory. It's written like this, and that is simply the number of elements in the set. So the number of coordinates, the number of pixels in our case. So that would be NA for set A and NB for set B, as I already used in these expressions. Some examples. If this is the set A, so all the white pixels are the object pixels, a translated version could look like this. It has exactly the same set of coordinates except that they are shifted to another location. This is an example of the complement of the original set A. And if this is set B, then for example, the union would be this. All the pixels that are either in A or in B or in both. This would be the intersection, and this is the set difference of A and B. All the pixels that are in A and not in B. With these definitions in mind, we can now define morphological operators. And the first one we're going to talk about is called dilation. Dilation of binary images. The definition of binary dilation is this. So if I have a binary image I, I'm going to dilate it. That's written like this, a circle with a plus inside. I'm going to dilate it with a structuring element, S. The formal definition is this, and in this lecture I'm always going to give you explanation in words as well. There you go. The dilation is the set of pixels for which the structuring element, if you shift that to the location X, so the point under consideration, and you reflect it, if you take the intersection with the binary image, if that intersection is not empty, then you add the pixel. So let's illustrate what that means. If this is the image, the binary image I, these are the object pixels, and now we need to define a structuring element. And a structuring element is very similar to a kernel in linear image filtering. You've heard the word kernel before in filtering. The structuring element in mathematical morphology is a similar kind of thing, except that the operation that we're going to apply is absolutely not linear, as you will see. So the structuring element could be this. Similar to a kernel, it's usually much smaller than the image. And in this case, we're looking at a structuring element of 3 by 3 pixels only, where the center pixel is the 0, 0 coordinate. So this pixel would be 1, 0 coordinate. This is 1, 1. And this would be -1, 0. So you can have negative coordinates as well. Now, let's do what it says here. We're going to shift the structuring element to the pixel under consideration and reflect it. But in this case, reflection has no effect because the structuring element is symmetric. So we can just look at the shifted version and take the intersection with the image, with the set of object pixels in the image. So we're going to construct a new image, and the way we do it is we shift the structuring element to each pixel. We're going to test each pixel. Is there an intersection of the structuring element with the set of object pixels in the image? And that is not the case for any of the pixels here because they're all background pixels. It's still not the case here, but when we hit this pixel, for example, which is a background pixel, if I would put the structuring element here, you would see there's an intersection with the set of object pixels, namely this pixel. So that means I'm going to put this pixel into the dilated image. Same for this pixel. It is a background pixel, but if I put the structuring element here, there's an overlap, there's an intersection with the set of object pixels. So I'm going to include this pixel as well in my dilated set. This pixel as well, this one not. If I would put the structuring element here, there's no overlap, no intersection, etc. So we test each and every pixel and see if there is an intersection. What we end up with then is this image. This is the dilated image of the input image shown on the left. And what we have done, we have added these pixels. All these green pixels were originally not in the set of object pixels, but they have now been added. And now you can appreciate why it's called a dilation, because the operator is dilating the original set. You're adding pixels to the set. Now we can talk about a second operator, which is erosion. The definition of erosion is I minus S, so that's written like this, a circle with a minus sign in it. S is the structuring element again. It's the set of all pixels X for which the structuring element shifted or translated to that position X is completely contained in the set of object pixels. Let's look at an example again. Here's another input image, binary image. These are the object pixels. I'm going to use the same structuring element for this example. And now we're going to do what it says here. We're going to shift the structuring element to the position X that we're going to consider, and we ask the question whether the structuring element at that position is completely contained within the set of object pixels. And that is not the case for all these pixels. Here we hit the first object pixel, but if I put the structuring element here, it's not contained completely in the set of object pixels. So that pixel is not included in my eroded set. Nor is this pixel, nor is this pixel, and you're going to go on and on, test all the pixels. This is the first pixel where if I put the structuring element there, it is completely contained in the set. So this pixel will be part of my eroded set. And this way we're going to test all the pixels. And what we end up with is this result. This is the erosion of the original image I. And what we have done essentially is we have removed these pixels shown here. These are all the pixels where if I put the structuring element there, the structuring element doesn't fit completely in the original set of pixels. And again, now you can appreciate why it's called erosion, because it's eroding the set. You're removing pixels. With these two basic operations, dilation and erosion, we can do a lot of very powerful image processing. We can combine these operators to obtain specific results, and I'm going to give you many examples of that. But first, let's talk a little bit more about these structuring elements. I've used one specific example of a structuring element, but the structuring element can have different shapes and sizes as well. This is the one I've used so far, but it can also be 5 by 5 pixels, 7 by 7, and bigger as you like. Structuring elements could also contain fewer pixels. So I used 9 pixels here, with this being the center pixel. But I could also use structuring elements like this. And when I show them like this, it means that these black pixels are not included in the structuring element, only the white pixels. So this would be an example of a smaller structuring element, but this one you can enlarge as well. And here are many other possible structuring elements shown. I have no idea why you would use these. Usually we limit ourselves to the symmetric 3 by 3 structuring element that I've used so far. I'm just showing this to make you aware that this is not the only possible structuring element. There are many other possible structuring elements that you could use for specific applications. Structuring elements can be decomposed dimensionally. For example, if I would dilate my image with a structuring element like this, that would be the same as first dilating with this one-dimensional structuring element, so that dilates in the x dimension, and then dilating the result in the y dimension. And the same for erosion. If you would erode the input image with this structuring element, that would be the same as eroding it first with this one-dimensional structuring element in x, and then eroding the result in the y dimension with this structuring element. You can also decompose structuring elements, larger structuring elements, in terms of smaller structuring elements. So for example, if I would dilate my image with this structuring element, that would be the same as dilating the image first with this structuring element and then repeating it 3 times. Applies to dilation and erosion. Okay, with all these basic definitions of set operators and the basic operators dilation and erosion, we can now do some more sophisticated stuff. So I'm going to show you a lot of examples of fun things you can do with these basic operators. The first is called opening of binary images. Again, first the definition. I can put the words here as well so you can read along. So it's denoted like this. The opening operator, opening an image with a certain structuring element, that is a combination of erosion followed by dilation using the same structuring element. An example. So here is a binary image. Suppose this is the output of a segmentation method, and you can see that it's not perfect. It has all kinds of false positives in the background that we may want to get rid of. If I dilate that image, this will be the result. I'm going to get rid of these false positive pixels, but I'm also going to lose, of course, pixels in my true object set. But if I now dilate this image again, I'm going to get back pretty much my original image, except for these false positive pixels in the background. They have been removed, and once pixels that are not connected to anything are removed, they will not come back anymore. So this is clearly an illustration of a nonlinear operation. What opening does is it eliminates details smaller than the structuring element outside the main object. That's opening, and now you can guess what is going to be the next operator we're going to discuss. That is closing. Closing of binary images. It's denoted like this, a closed circle. So the closing of image I with structuring element S is defined exactly as the opposite of opening. It's first a dilation and then an erosion. Again, an example. If this is the image that we're going to start with, the segmentation result, in fact, it is the output of the previous step where we got rid of the false positives in the background. If we dilate that image, we are going to get this result where many pixels have been added, which resulted in a closing of the hole in the set. But also we've added many pixels at the boundary of the object. And that's what we don't want, of course, so we can get rid of that by the erosion step. Now we have a result where the holes have been closed. So what closing does is it eliminates details smaller than the structuring element inside the main object. And you can combine opening and closing, as you've seen from this example, to get rid of both false positives in the background and also false negatives within objects. So it's a way to post-process segmentation results to reduce the false positives and false negatives. Another thing we can do is morphological edge detection. That is the difference between the dilated and the eroded image. Let's look at this example. If this is the object set and I apply dilation, I will get this set. I could also apply erosion and I would get this set. And if I take the set difference, I will get this result, where you see that all the green pixels are the ones that have been added by the dilation step, and all the red pixels are the ones that have been removed by the erosion step. So these are what you could call the outer edges and the inner edges. In other words, the green pixels are the original background pixels that are connected with the object pixels. And the red pixels are the original object pixels that are connected with the background pixels. So you could take either one of those. That's shown here. How do we get a 1 pixel thick outline of all objects in a binary image, such as this one? Well, you simply dilate the image, for example, and subtract the original, and then you have all the outer edges of the objects. And in a similar way, you could get the inner edges. Then you would take the input image and subtract an eroded version of it. This is a way to do edge detection in binary images. It could be done as a pre-processing step to compute the length of the contour by pixel counting. Another thing we can do is called reconstruction of binary objects. How do we create an image containing only the selected objects? Let me explain in words how this works, this algorithm. You create a marker image called R0 containing the seed pixels from each selected object of an image I, and then we iteratively compute Ri, where I is the iteration number. So what we do is we take the previous result, dilate it with the structuring element, and take the intersection with the original image. And we continue doing this. This is an iterative process until there is no more change from one iteration to the next. Let's have a look at how this works out in practice. If this is my image, and suppose that I would be interested in these two objects of interest. So I want to end up with a binary image that has only these two objects in them, only these two sets of pixels, and not the others. I can click, for example, 2 points, use them as the seed points in this algorithm, and then I'm going to iteratively dilate these seed pixels, dilate these sets. But after every dilation, I take the intersection with the original image. So that means that this seed pixel will start growing, you start adding pixels, but after every iteration, you remove any pixels that would be outside the original object. So in some iteration, no further pixels will be added, and then you stop the process. And the result is an image that has only the two objects of interest. And now I can do further measurements, for example, what is the area of these objects of interest, etc. Another thing we may want to do, for example, is remove objects that are only partly in an image. What we can do is take the boundary pixels of an input image as the seeds, and then compute the reconstruction, as we've just defined in the previous slide, the reconstruction from those seeds, and subtract the result from the input. Let me illustrate that. If this is the input image, it contains many objects. Suppose these are cells, and I would be interested in knowing what is the average size of the cells, for example. If I would do this measurement from this image, after I've run a connected components labeling algorithm, so each connected set of pixels is uniquely labeled, the problem would be that I would include in the measurement all these cells that are only partly contained in the image. So that would bias my measurement. For example, this cell has only a very small area according to the portion that is in the image. But that is not the actual area of the cell. So I want to exclude from this image all the objects that are touching the boundary of the image. So let's go through this procedure. We take the boundary pixels of the input image as the seeds. So we're going to construct an image B where you see here, these are the pixels at the boundary of the image that belong to any one of those objects that are touching or overlapping with the boundary. We take those as seeds, and now we're going to do a reconstruction, just like we did in the previous slide. We reconstruct from these seed points the cells that are touching the boundary. Once we have this image, we can subtract it from the original set, and that will give me this output image, which has only the objects that are fully contained in the image. And now my measurements will not be biased anymore. Another thing we can do with reconstruction is fill all the holes in the objects. I've already given you one example of how you might fill holes simply by using the closing operation, so the combination of dilation and erosion. But that works only for small holes that are smaller than the structuring element. So how do you get rid of bigger holes in objects? The way it works is you take the complement of the image, take the boundary pixels as seeds, just like in the previous slide, compute the reconstruction of this complement from the seeds, and then take the complement of the result. Let me illustrate that. If this is my input image, I found all kinds of objects, but these objects have many holes, and these holes are pretty big. If you would apply the closing operator here in an attempt to close the holes, you would need a pretty big structuring element. Probably too big, because it would be so big that it would also connect objects that are close to each other. So that's not really going to work very well. But we can use this trick as explained here. We can take the complement, so that's all the pixels that are originally background now become object, and vice versa. We take the complement and then we take the boundary pixels, which are all the pixels in this case at the boundary, as seed points, do the reconstruction, and that will reconstruct this huge white space over here. But you will not be able to penetrate into the objects. So the results of this reconstruction operation will be this. And now you simply take the complement of that reconstruction, and you end up with an image that has all the objects with the holes closed. Another thing you can do is compute the distance transform. How do we compute the distance of object pixels to the background? Well, you could, for example, iteratively compute eroded versions of images, where I is the iteration number. So at every iteration, we're eroding the image from the previous iteration. And at every iteration, you set all pixels that are eroded in iteration I to the value I in the output image. If this is my input image, and I do this iteratively, erode, and at every iteration, I'm going to label the pixels with a value equal to the iteration number in which they were eroded, I end up with an image like this. In this image, the pixel value at every pixel is now essentially the distance to the nearest background pixel. That's why it's called a distance transform. Another operation that's very useful is called ultimate erosion of binary images. That gives you the center points, or the center blobs of points of all objects. And you can obtain this from the distance transform. You compute the distance transform of the image, and then you find all the local maxima in the distance transform. So this is the same as keeping only the last object pixels before erosion. If this is the input image, I can compute the distance transform, and now the local maxima are now the center points of the objects. And we can use these as seed points for some further processing. For example, to separate objects that are touching each other. Perform ultimate erosion and then perform a reconstruction of the result but with the additional constraint that the objects may not merge. If this would be the result of a segmentation, let's say I've developed a cell segmentation method and for a particular image it gives this result, and you can visually guess that these are different cells, right? But they're all connected. So if I would run the connected components labeling algorithm, it would tell me this is one object. And if I would then do measurements like what is the area of the cells, I would get a completely wrong answer. This is a clear example of where you would need to do some post-processing of the segmentation result to separate touching objects. You can compute the distance transform of this image. You take the object centers, the peaks of the distance transform, and you use those as seed points for a reconstruction process with the constraint that objects may not merge. So you dilate these seed points iteratively, but you don't allow objects to grow into each other. As you can see here, this was originally one object, but by taking the distance transform, we get 4 peaks and we get 4 seed pixels. Okay, so at this stage, it has already been recognized that these are actually 4 objects. If we now do the reconstruction process with this additional constraint, we end up with this image where these 4 objects are now nicely separated. And if I would now run the connected components labeling algorithm, I would get 4 different objects. And my measurements are not biased anymore. Here's an important remark. Since elongated objects may result in multiple local maxima, this approach that I'm showing here works best for objects that are more or less circular. It's used a lot in cell segmentation because cells are more or less circular objects. This was an example of how you can use ultimate erosion. We could also think about ultimate dilation. How do you find the background points that are equidistant to the objects? Well, you can iteratively dilate the image while imposing this non-merging constraint that I mentioned. And what that will give you is what is called the Voronoi tessellation of objects. If this is my input image and I would iteratively dilate these objects, but I don't allow them to grow into each other, just like I did in the previous example, then I would end up with an image like this. Every one of the black pixels here in this image is now equidistant to the nearest objects, which you can appreciate from this visualization where I've overlaid the original objects. So you can clearly see that every pixel here has the same distance to this object as to this object, for example. Another thing you could do is called skeletonization. How do you find a representative center line of the objects of interest? Iteratively apply conditional erosion, thinning, that does not break the connectivity of the result and does not remove single pixels or end pixels. If I have an image like this, which is a segmentation of a neuronal cell, so from a microscope image, you see the cell body and lots of extensions here, the dendrites. If you would want to have a 1 pixel thick representation of all these dendrites, which could be useful, for example, if you want to measure the lengths of these things, then you could do this operation. Conditionally erode ultimately until you have a 1 pixel thick representation. This representation is also called the skeleton. So this is why the operation is called skeletonization. So far I've shown examples of binary morphology of 2-dimensional images, but you can extend all these concepts to n-dimensional images as well. They extend to any dimensionality. For example, this is a visualization of a 3-dimensional binary image. And all these elements are called voxels now, volumetric pixels, you could say. Structuring elements, you can extend them to 3D. The original 2x2, in the case of 2 dimensions, could become 3x3x3. And you could do 3D dilation, 3D erosion, opening, closing. And all the algorithms I just explained, you can also do in 3D and in 4D, 5D, if you would have an application where this is useful. That's what I wanted to tell you about binary mathematical morphology. We're now going to switch gears and talk about grayscale mathematical morphology. The way we can do grayscale mathematical morphology is by considering n-dimensional grayscale images as n+1 dimensional binary images. Let me show you what I mean by that. If this is my input grayscale image, a 2-dimensional image, where every pixel has a particular gray value or intensity, I could represent it as a 3-dimensional binary image, like this, where you see all these columns here At every pixel, x and y, there's a column with a height equal to the gray value in that pixel in the grayscale image. And this representation is called the umbra of the image, u of I. The transformation from the grayscale image to the binary image is called the umbra transformation, and the inverse takes you back from the higher dimensional binary representation to the lower dimensional grayscale representation. And with this concept in mind, we can do grayscale mathematical morphology using binary morphological operators. Simply transform the image to a binary representation, do the binary mathematical morphology here, and then transform back to the grayscale domain. So now let's revisit some of the concepts we've discussed in the binary case. For example, dilation. How can we dilate a grayscale image? We use the same definition, we use the same symbol, because essentially it is the same thing. It's the same kind of operation, except that now we're doing the dilation in the umbra representation of both the image and the structuring element. And then we take the inverse of the result. Let me illustrate how that works with a practical example. And since it's a little bit complicated to show three-dimensional binary images, I'm going to reduce the dimensionality of the whole discussion by 1. So we're going to look at one-dimensional grayscale images which transform into two-dimensional binary images. Here's an example. If this is my one-dimensional input image, I can do this umbra transformation. That will give me this two-dimensional binary image. And this lowest row is the 0th row. So this is the 0, 0 coordinate, which means that if a pixel would be black, would have value 0, then the corresponding column in the binary image would still have one pixel that is white, that is object pixel. And then we have the structuring element. This is an example of a structuring element. That is also a grayscale image, in this case one-dimensional. And that transforms into this umbra representation. And like I just explained, in this case the values are actually 0 here. So what that will give me is a binary structuring element that looks like this. 3 pixels are on, this is the central pixel. The dilation of this binary image with this binary structuring element is this, where I've added these pixels. And now I can take the inverse umbra transformation, and that will take me back to the grayscale domain. So this is now the grayscale dilated version of the input image, where you see that many pixels now have a higher intensity, a higher gray value than in the original image. One important note here about the structuring element. We have a grayscale structuring element. Any kind of grayscale structuring element could be used. But what we will be using here in this lecture is only the flat structuring elements. So meaning they have only values 0 in them. So they transform to one-dimensional umbra representations. And this is what is used most often for grayscale mathematical morphology. Now look carefully what we have done here. These green pixels are the ones that were added in this dilation process. And what this is equivalent to is that for every column, we look at the neighboring columns and we replace the original column height with the highest of the neighboring columns. So for example, for this column, this was the original height. And we look at the neighboring columns, this one, and we observe that this one is the highest. So we make this column of the same height as well. That's what happened here. That is in effect what this dilation does. It replaces every column with the highest of the two neighbors and the column itself. So you just look at what is the highest and you replace the current column with the highest column. So this column becomes as high as this one. That's what you see here. All these pixels were added. This one becomes as high as this one. All these pixels are added. Same for this one. And in this case, you can see that for this column, for example, if you look at this column's height and the height of its neighbors, you see that this column is already the highest, so nothing changes. It keeps its original height. What this translates to is that we're taking a local maximum. If you translate this to the grayscale representation, what we are doing is for every pixel, we replace it with the largest value in its neighborhood. So that's an alternative definition of what grayscale dilation is. The dilation of an image at any pixel x is the maximum of all the pixels in a certain neighborhood with spatial extent equal to that of the structuring element of the image plus the value of the structuring element. But since the value is always 0, the grayscale value of the structuring element is always 0, it is literally taking the maximum of the image pixels. Here's an example of the effect of this operator. If this is my original grayscale image, and if I would use a structuring element of 7 by 7 pixels, a flat structuring element, so the value is 0, so in this addition nothing is added, we're literally looking at the maximum value of the local image pixels. Then the grayscale dilation, the local maximum operator, would give this result, where all the small black spots have now been removed. We can also define erosion this way. Erosion is now, you take the umbra of the image, the umbra of the structuring element, and you do a binary erosion, and then take the inverse umbra operator, and that gives me the grayscale eroded version of my input image. Again, a one-dimensional example, the same input image as I showed before, translates to this umbra representation, this two-dimensional binary representation. If I take the same structuring element with zeros everywhere, so the flat structuring element, that transforms to this umbra representation, and now I can do a binary erosion, and that will give me this final result, where all these pixels have been removed. Transforming this back to the grayscale domain gives me this final output image, where you will now appreciate that many pixels have a value that is lower than the original input image. Again, any grayscale structuring element is possible, but we use, in this lecture at least, and in many applications, people typically use the flat structuring element only. And same as for dilation, let's have a look at what actually happened here. For dilation, we were replacing each column with its local maximum. Erosion does the opposite. It replaces each column with its local minimum. Let's look at this column, for example, this third column in the image. You look at the height of this column and of its neighbors, and you see that this neighboring column has the minimum height, so this column also gets the same height. That's what you see here. And the same for all the other columns. So in effect, what this operator does is it takes a local minimum. And that is the alternative or equivalent definition of grayscale erosion. It takes the minimum over a neighborhood of pixels of the image minus the structuring element. But again, since this is a flat structuring element, it's always 0. And we're literally looking at the minimum of the image pixels. The effect is that if this is the input image, and I would again look at a structuring element of 7 by 7 pixels, a flat structuring element, the erosion would give me this result, where now all the bright spots have been removed because we take a local minimum everywhere. We talked about opening of binary images, so we can also do an opening of grayscale images. You combine the erosion and the dilation operation, but now in the grayscale sense, as I've shown on the previous slides. If this would be my input image, a grayscale image with lots of noise, both in the objects and in the background, if I would take a small structuring element like 3 by 3 pixels, and I would perform this opening operation, this would be my result. And as you can see, the image has been smoothed in a way. There's not as much noise in the background anymore, and neither within the object, but the noise has a different structure now. You can also do grayscale closing, same definition as for binary closing. First do a dilation, then an erosion. So if I would look at an inverse of the image I showed in the previous slide, and I would use a structuring element of 3 by 3 and apply closing, I would get this result, where again a lot of the noise has been removed, both in the background and in the objects. Again, it's a smoothing operation. With morphological smoothing of grayscale images, we can suppress image structures of specific size and shape as well, if you would adapt the structuring elements to the type of shapes you want to remove. So high valued bright image structures are removed by grayscale opening, as I've shown, and low valued dark image structures are removed by grayscale closing. Here's an extreme example. This is an artificial image, just for illustration purposes. The opening of this image with a structuring element of radius 7 pixels would give me this final result, where the smoothing is clearly very non-linear because a lot of the noise has been removed. But look, also the objects that are smaller than this size of the structuring element have also been removed. And if I would increase the size of the structuring element, for example, to 25 pixels, I would get this result, where now a lot of things have been removed, except for the objects that are larger than this structuring element. And this clearly shows you how non-linear these operators are. There is no way you could get an image like this by linear filtering operators. This clearly shows that these operators are highly non-linear. You're really removing image information and only keeping the image information of interest. So these are very powerful operators that can be used to pre-process images to make the subsequent segmentation step easier. Other things we can do with grayscale mathematical morphology is compute the gradient of grayscale images. In a previous lecture, we've explained how you can compute the gradient using linear filtering, computing the derivatives in x and y of an image. The morphological equivalent is that we compute the difference between the dilated and the eroded image. If this would be my input image, which I've shown before a couple of times in other slides, you can take the dilation, the grayscale dilation, and maybe you don't really see the difference, but it's slightly different. The intensities are slightly higher here. You could also look at the erosion, and if you would subtract the two, then you would get what is called the gradient image, the morphological gradient. And here as well, we can talk about the concept of outer gradient and inner gradient, similar as for the binary case. So if we look at the dilation and the erosion, and you would take the difference between the dilation and the input image, or the difference between the input image and the erosion, you get the outer and the inner edges, you could say. This can be nicely illustrated by using color coding. If we color code this image in green and this image in red, and we would overlay the two images, you can nicely see the outer and the inner edges. If you zoom in, for example, on the ear here, you can see that the edge pixels from this image are the outer edge pixels, and the pixels from this image are the inner edge pixels. We can go one step further and compute the Laplacian as well, the equivalent of the second order derivative image of grayscale images. That's simply the difference between the outer gradient and the inner gradient. If this would be the outer gradient, the dilation minus the input image, and this is the inner gradient, the difference between the input image and the erosion, then the difference between the two looks like an image that is very similar to a Laplacian image that you would get with linear operators with second order derivatives, as we talked about before. Here's a graph that gives you a little bit more of a theoretical sense or explanation of what is going on. A one-dimensional profile. If the black line is the input profile, and I would do a dilation of that profile, that means I would look at the local maximum at every position. That is going to shift my curve to the left, because for every position, for every x position, the value is going to be higher than the original. It's going to be the local maximum of the input curve. And the erosion is going to shift the input curve to the right because it is the result of taking a local minimum. And now, if we take the difference between the two, you will get a profile like this. So this is equivalent to the gradient of this black curve. And if you would take the difference between the outer edges and the inner edges, which is equivalent to taking the dilation plus the erosion and minus 2 times the input image, that would give me a profile like this, with a maximum here and a minimum here, and that is equivalent to the second order derivative, or the Laplacian image. Some more operators that I want to show you. One of them is called the top hat operator, or top hat filtering of grayscale images. This will be familiar to you. If this is the input image, which contains a lot of black spots that I may be interested in measuring, but in the background there's a kind of shading which may interfere with the measurements. So I need to get rid of this background shading pattern. And the way to do that is to estimate the background and then subtract it from the input image. So I can take the dilation with a structuring element that is big enough to get rid of these spots. In this case, I've taken a structuring element, a circular structuring element with a radius of 10 pixels. That gives me this image. But now all the intensities are overestimated because you take the local maximum all the time. That's the equivalent of dilating. And to compensate for that, you need to do a subsequent erosion. It looks almost the same visually, but the intensities here are closer to the background intensities in this image than compared to the dilation. So now we have a good estimate of the background. Together, this is called a closing operation, as we've explained, and you can now subtract this image from this image, and that will give me this output image, where the shading in the background has been removed, and I keep only the relevant image intensity information. It's illustrated in a bit more detail here. If this is the input image, if we look at a scan line, for example, this blue line here, the intensities would look like this. So it's noisy, obviously. And these dips here in the profile correspond to the spots. If I dilate this image, I take the local maximum everywhere, that will give me the red profile, which you can see as an overestimation of the background. And so I need to correct for that. I take the erosion, and now the green profile is the final result that you can subtract from the blue profile. And of course, because the green profile now always has a value that is higher than or equal to the blue profile, we're going to get negative results. So you need to compensate for that by adding the maximum possible value of the input image. If it's an 8-bit image, that's 255. And so then if this would be the original profile, and you subtract the green profile I showed on the previous slide, you will get this final red profile. The last thing I want to explain is the H-dome filter of grayscale images. The idea is to find regional maxima using morphological reconstruction. We've talked about this reconstruction operation before for the binary case, but we can do the same thing for grayscale images. You create a seed image, R0, by subtracting from the input image I a constant value, H, and then iteratively compute Ri as the minimum of a dilated version of the previous iteration and the original image. This is very similar to the binary case I explained before. And you iterate until there's no more change from one iteration to the next. If this would be my input image, where you have many different objects, it's very noisy, there's also a shading in the background, and if I would be interested in measuring these objects of interest, then the noise and the shading will no doubt interfere with my measurements. So I need to clean up this image to get rid of these artifacts. The image R0 would look like this. That is simply the input image, but with a constant value subtracted from it. And the result of this reconstruction process is shown here on the right. Let's have a look at the profiles in these images along a scan line to get a better understanding of what is going on. If we look at a scan line in the original image, this blue scan line, this would be the intensity profile, the blue profile. And you can see this effect of the shading pattern in the background. It's going up in the middle and it falls off on the sides. The same scan line in the seed image is the same profile, but then lowered by H, which in this case is 50 intensity units. So it's exactly the same profile. And the result of the reconstruction process is the red profile shown over here. And you can appreciate what this operator has done now. It has basically taken the regional maximum everywhere. This peak in the green profile is now extended to this region. The peak in this part of the profile is now extended to this region, and the same for this region, this region. So what this reconstruction computes is an image showing the regional maxima. And that is a good estimate of the background that we can then subsequently subtract from the input image. And the result is called the H-dome image. If this is the input image, again, I compute the reconstruction, subtract it from the input image, and I get an image where all the background artifacts have been removed, and I keep only the objects of interest, and all of them have an image intensity that is at most this value H. Looking at the profiles gives you a better understanding of what is happening. Here again is the input profile, the blue one. The red one is the reconstructed profile. And you subtract the red from the blue, and that will give you the green profile. This is the subtraction image, where the regions now have at most an intensity value of H. This is a great pre-processing step for subsequent segmentation by, for example, thresholding. If you look at the original profile, there's no way I'm going to get all the objects of interest by thresholding this profile. If I would put my threshold here, I would get these objects, but not these ones. They're below the threshold. If I would lower my threshold, for example, to 100, I would get this object as well, and this one, but this is going to be one object now, you see? So thresholding is not going to work because of these background artifacts. And that's the last thing I want to illustrate here. If this is the input image, an artificial image, just to illustrate the point I want to make, where you have all kinds of objects, both in the background and within, for example, a cell. Suppose I'm interested in segmenting all these objects in the background and in the cell. There's no way I can do that with a simple single threshold. Because if you look at an intensity profile, it looks like this. If I would threshold at an intensity of 25% of the dynamic range, so at a quarter here, I would get the objects in the background, but the cell itself gets segmented as one big object, and you would not be able to separate the individual objects within the cell. If I would increase the threshold to 50% of the dynamic range, you start to see all kinds of artifacts. If you increase the threshold to 75%, I nicely get all the objects within the cell, but I've lost all the objects in the background. There is no single threshold that's going to do the job here. But if I compute the H-dome image of this input image, as shown here, now the intensity profile looks like this, and I can apply thresholding at 25%, for example, to get all the objects of interest I wanted. And it would be stable even if I would increase the threshold. Of course, at some point the results start to degenerate, but you get the idea. It's much easier to do a good segmentation in this image than in this image using thresholding. All right, that's what I wanted to explain to you in this lecture. Mathematical morphology provides a powerful toolbox of methods around segmentation. So before segmentation, you could use grayscale mathematical morphology as a pre-processing step to remove grayscale noise, background shading, as I've shown, or other unwanted image structures. Or you could use binary mathematical morphology as a post-processing step after segmentation. For example, you could use it to close holes in objects and the background, find the inner and outer outline of objects, detect and separate touching objects, extract representative shapes, and compute distances, etc. And that's it for this lecture. I'll see you in the next lecture.